What we're going to do is talk about relative importance analysis and then go through an example. Relative importance analysis is a very helpful and insightful supplement to multiple regression analysis, but it does require us to have some conversation before we go through it so that we can understand what we're doing, why we're doing it, and then how the software is performing the analysis. When we perform multiple regression analysis, we're often doing it for one of two reasons. First is that we're interested in examining and explaining a set of predictors that maximize the variance explained in the dependent variable. When we do that, we're often focused on examining the R-squared of the model, right? The coefficient of multiple determination. R-squared is a measure of how close the data are to the fitted regression line. It's computed by explained variation divided by total variation, so it's always going to be between 0 and 100%, with higher numbers indicating the model does a better job of explaining the variability in the dependent variable. The second reason we perform multiple regression analysis is because we're interested in understanding how much of the variance in the dependent variable can be attributed to a particular predictor variable. This is very important. When we're focused on understanding how much of the variance in the dependent variable can be attributed to particular predictor variables, we key in on the significance of the coefficients, their direction, and the magnitude. So for analysts and researchers, this is really insightful and important to understanding what variables are significantly associated with our dependent variable, and also what variables have the greatest impact on our dependent variable. Right? So we might have multiple variables that are significantly associated with our dependent variable, but maybe some of those impact our dependent variable more than others and may also be easier to manipulate and therefore might be the focus of any recommendations and suggestions we would make. Now, of course, in multiple regression, there's going to be a lot of different predictors in the model. That can introduce some challenges and some problems, as I'll talk about in a little bit. So the regression coefficients are often looked at as means of understanding what variables have the greatest impacts on the dependent variable. A regression coefficient helps us understand what happens to the dependent variable when we increase the predictor variable by 1, holding the other predictors constant in the model. Okay, now unstandardized coefficients represent the variables as they are. So we might have variables that have different metrics in our analysis. We might have a variable that is measured from 1 to 7 and another variable that's measured from 0 to 100. Now, the different scale that these variables are on can impact the unstandardized coefficients. And so it can make it difficult for us to make inferences regarding how much of an impact relative to the other a particular variable has. And so researchers will often standardize the predictor variables. And so we can standardize variables by subtracting the mean and then dividing the new value by the variable's standard deviation. So it's going to result in a mean of 0 and a standard deviation of 1 for a variable. And so we do this because now we've put everything on the same scale, right? It didn't matter that our two predictor variables were measured using different scales. Now they both have a mean of 0 and a standard deviation of 1, and that can permit us to make inferences regarding the relative effect of one versus the other. Here we're predicting marketing cost, and we have our intercept, the constant, and we have our packaging, our transformation, our loading and unloading, commission charges, rent, electricity, and labor as our predictor variables. You can see that we have our unstandardized coefficients and we have our standardized coefficients. Now, I want us to assume that these variables were measured using different scales. So maybe some of these were 1 to 7, some of these might have been 1 to 100, and some of these, like rent, electricity, and labor, could actually be a dollar amount. And so it's going to make it very difficult for us to compare the impacts that these have on marketing cost using the unstandardized coefficients. We could get around that issue by standardizing these predictors and looking at their impacts on marketing cost. Fortunately for us, statistical packages will generate the standardized coefficients. And so by looking at the standardized coefficients, we can make some inferences regarding which variables have the greatest impacts on the marketing cost variable because we've standardized those variables. But there's a problem that we can run into when we rely on standardized coefficients to make inferences regarding what predictor variables have the greatest impact. And what's particularly important here is that when the predictor variables are correlated with one another, that is, to the extent to which the predictor variables move up or they move down together, the accuracy of the significance, the direction, and the magnitude of the coefficients is going to decrease. Hence, collinearity can be really problematic. Let me explain this to you a little bit more. So I've given you visual illustration here. We've got an example of low collinearity where the predictor variables only have a little bit of overlap. And then we have an example of high collinearity where the variables have a large amount of overlap with one another. Now, in the low collinearity example, we can feel more confident that any coefficients are going to be attributable to the predictor being examined. But in the high collinearity example, we can't really feel that confident that the coefficients we're observing are actually attributable to the predictor being examined. Let me share an analogy that maybe help clarify the situation. And so I want you to assume that you're going to, say, a rock concert, and you have two guitar players, and you want to determine which guitar player plays best. Well, on stage, they're both going to be playing at the same time. They're probably going to be moving around. They might be aggressive with how it is that they're playing. And it could be difficult for you to accurately determine which guitar player is creating the sound that you're hearing. And therefore, make it difficult for you to determine which guitar player is playing best, even if they're playing different notes. This is a very similar thing to what's going on when we have predictor variables that are very highly correlated. It's very difficult for the model to partial out the variance in the dependent variable that's uniquely attributable to each predictor. One is that the coefficient might not be statistically significant, even if we think it should be. Second could be that if we add or we delete a variable, the regression coefficients change dramatically. You also might see a negative regression coefficient when you think you'd have a positive one, and vice versa. So analysts will often look at the correlations amongst the predictor variables to determine if multicollinearity is a problem. Usually, when collinearity levels are above 0.8, then analysts say that they have an issue. Analysts will also look at the variation inflation factor, which is generated in the regression analysis itself, to determine if collinearity is a problem. And it's generally believed that variation inflation factors above 5 are problematic, but even at levels above 4 can create some issues. Now, the challenge is that when you have many different predictors in the model, what's required to have multicollinearity become problematic varies quite a bit. And so if you have high correlations of 0.4, 0.5, and you have many different variables in your model, well, it's going to be very difficult for you to be confident that even with those levels, that you're being able to attribute the unique variance explaining the dependent variable to a particular predictor variable. And so relative importance analysis is a really helpful means of performing a supplemental analysis so that you can better infer which predictor variables are explaining the variance.